Hi friends, welcome back in this series of featureization and model tuning. Today we will see one case study on linear regression. Basically, we have seen auto MPG dataset various times to perform some operations or any algorithm in it. So today as well we will do the same with the auto MPG residual, right? So before wasting time, let's start. So again from starting, we are importing the matplotlib inline, right? What it will do is it will plot all the graphs in Jupyter notebook itself. Then we are importing numpy as np, right? It is nothing but the numerical libraries. Then we are importing linear regression for machine learning library, right? From sklearn or linear regression, importing linear regression. Then to handle data in form of rows and column, we are importing pandas as pd. Now importing plotting libraries, so import plotlib, matplotlib.pyplot as plt. Similarly import matplotlib.style, right, for our styling thing. Now plt.style.use, so classic style we are applying here. Then we are importing seaborn for statistical plot, so import seaborn as sns, right? So now the time is to import our car mpg csv, which I'll also provide the link for it in the description, right? So first we will do check top 50 rows, right, to get the again feel of the data structure. So here you can see that we have the same data structure that we have already discussed in the last videos. So mpg, cyl, disp, hp, right, horsepower, wt, acc, year, origin, car type and car name, everything is there regarding vehicle. Now drop the car name column as it is useless for the model. So again mpg miles per gallon df, right? So mpg df dot drop, we are dropping the car name, completing dropping the column itself. Now mpg dot df, so if we get the df, so here you can see that the car name column has been removed. Now replace the numbers in categorical variable with the actual country names in the origin column. So mpg df origin, right? mpg df origin dot replace 1 for America, 2 for Europe, 3 for Asia, right? Now mpg df, so mpg cyl, disp, hp, wt, acc, year, origin, car type, so everything is there, right? You can see here. Now convert categorical variable into dummy indicator variables, as many columns will be created as distinct value. This is also known as one hot coding, right? So the column names will be America, Europe and Asia with one hot coding. All right, so to do that, mpg df equals to df pd dot get dummies, right? mpg df columns we are passing origin. So now mpg df, so here you can see that all the column that we are getting here, all the rows for them, right? Now let's analyze the distribution of the independent mpg column. So here mpg df dot describe, right? Here I'm doing transpose, so it will return all the description regarding the mpg dataset. So here you can see that count, mean, standard deviation, minimum 25. These are nothing but the interquartile ranges, and with respect to all our columns. Then we are printing the data types by using mpg f.d type. So here you can see all the data type that we are getting: mpg, cyl, disp, hp, wt, accumulator, year, so on so forth, right? Then here's one note we have is to that hp column is missing the describe output, so that indicates something is not right with the column. So here check if the hp column contains anything other than digits, right? So what we'll do is run the isDigit command here, right, to check hp column of the mpg df data frame, and result will be true or false for every row capture, right? So the result in temp data frame, and do a frequency count using value counts, right? So there are basically 6 record with non-digit values in hp column. So let's start, like temp equals to pd dot data frame, right? mpg dot df mpg df dot hp dot string, right, dot is digit. So here if the string is made of digits, store true, otherwise it will store false in temp data frame. Now temp hp equals to false, so from temp take only those rows where hp value is false. So here you can see that we are accessing in temp side, right, access only those values. So here we are just passing the condition temp of HP equals to false. So here you can see all the false value that we have here. Now on inspecting a record number 32, 126, etc., we find some question mark and in the column, right, replace with none. So replace them with none and remove the record from the data frame that have none. So mpgdf equals to mpgdf dot replace, right, we are replacing this question mark with np dot none. Now let us see if we can get those record with none. So mpgdf, right, mpgdf dot is null dot any access equals to 1. So here we will get mpg cyl disp hp wt acc year car type origin America, origin Asia, origin Europe, all these things, right. Now there are various way to handle missing values. So drop the rows, replace missing values with median values, etc. So here we have nearly the out of 398 rows, 6 have none values, right, in the column HP, and we will drop those 6 rows. Not a good idea under all situations. So here what we can do is HP is missing because of the non-numerical values in the column, right. So here non-numerical values in the column. So now instead of dropping the rows, let's replace the missing values with median value. So here mpgdf dot median, so if we call it, so mpg cyl disp, everything we have here is right, you can see here. Now replace the missing values in HP with median value of HP. Note, we do not need to specify the column names. Every column's missing value is replaced with that column's median respectively. So access equals to 0 means column wise mpgdf dot fill na, mpgdf dot median. Now mpgdf equals to mpgdf dot apply lambda, right. If we apply lambda here for x in x dot fill na and x dot median, we are doing it for access 0, right, for all the rows. So mpg, if we get the data type, so first we are getting all the data type. Now mpgdf of hp, right, equals to mpgdf hp dot as type float 64, because here you can see that the hp is still we have is object. Now we are converting it to float type by just using as type. Now mpgdf dot describe, so if we call it, so here all that you can see mpg cyl disp hp wt acc year car type origin America, origin Asia, origin Europe, right, and then we have count, mean, standard deviation, minimum, and all these interquartile ranges, so on so forth. Now let us do a correlation analysis among the different dimension and also each dimension with the dependent dimension, right. So here what it is telling that this is done using scatter matrix function, which creates a dashboard reflecting useful information about the dimension. The result can be stored as a png file, of course, and the file can be opened easily. We can also paint to get a larger viewer. Now mpgdf dot attribute, right, mpgdf attribute equals to mpgdf dot ilog. We are accessing all the rows from 0 to 9th column, right. So here you can see sns dot pair plot mpgdf attribute diagonal kind, we are passing kd. So here to plot density curve instead of histogram. So now you can see that this is the scatter plot that we have for all these mpg cyl disp, right, and with respect to all these mpg cyl disp and so on so forth. Now what the observation that we are getting here is that the data distribution crosses various dimensions except ACC do not look normal. So here are ACC, it is this one, right. So ACC do not look normal. So here was the ACC. Now close observation between MPG and other attribution indicate the relationship is not really linear. So relation between MPG and HP shows heteroscedasticity, which will impact model accuracy. So how about the MPG versus year? So if we see the MPG versus year, this one, right. So here surprisingly is to see the positive relation that we are getting, the MPG and the year, or the MPG and the here, right? So this is the relationship. Here you can see that, and here you can see that. Now copy all the predictor variable into X data frame. Since MPG is dependent variable, drop it. So what we'll do is X equals to MPG df dot drop MPG, X is equals to 1, X equals to X dot drop, origin is camera, origin Asia, origin Europe, and X is equals to 1. Now copy the MPG column along with along into the Y data frame. So this is the dependent variable, basically Y equals to MPG df, right, of MPG. Now let us break the X and Y data frame into training set and test set. So for this we will use a sklearn package, right, data splitting function which is based on random function. So from sklearn.model selection import train test split. Now split X and Y into training and test set in 75/25 ratio. So X train, X test, Y train, Y test, all that we have. Train test split X, Y, test size, right, 0.30, and the random state equals to 1. Now invoke the linear regression here, but this one, invoke the linear regression function and find the best fit model on training data. So again, to get that, we are just calling regression model, linear regression function, right, fitting the linear regression on our X train, Y train that we just got from here. And then let us explore the coefficient for each of the independent attributes. Right here, for idx column name in enumerate xtrain dot column, print the coefficient for all these braces dot format. So column name, regression model of coefficient, so 0 of idx, so all that we are getting, right? So you can see the coefficient for CYL is this one, for DISP is this one. So if we check, the highest correlation that we are getting is for car type, that is 6.62, right? And similarly then we can see it is for CYL. Now let us check the intercept for the model. So intercept equals to, again, regression model dot intercept 0. So the intercept for our model is we are getting minus 60.69. So if we check the score of our regression model, so by passing X train, Y train into regression model dot score, so we are getting nearly 82% of the score. Right now, the score of our X test, Y test, again it is we are getting for 84%. So is OLS a good model, right? So should we building a simple linear model? Check the residual for the predictor. So figure that we have is plt.figure, fixed size we are passing when 10/8. Now the SNS resid plot, so X equals to X test HP, then we are getting Y equals to Y test of MPG, color green, loss equals to true, right? Now figure equals to plt dot figure, fixed size 10/8, again a resid plot. So here you can see that we are getting is for X test, Y test, this one, right? This one's for MPG, and this one with respect to HP, and this one with respect to ACC, right? So here you can see that the resid plot that we got here. Now, so the model explain 85% of the variability in Y using X, right? Where it is. So using stat model library to get R type output. So again, for that we are concatenating our X train, Y train, right? And X is equals to 1, then data we are getting all these concatenated value. Okay, now importing stats model dot formula dot API SMF. So here, right, so basically the management frame, or we can say, or facility. So LML equals to smf dot ols formula, we are passing MPG, the tilt, right, CYL plus this plus all these are adding. Now data equals to data train dot fit, so LML dot parameter. So if we get that, you can see the intercept is again minus 26, right? And all these for CYL, DISP, HP, so on so forth. Now here we are getting the inferential statistics, right? So here you can see that OLS regression result is there, right? And if we check the model, that is OLS, right? Similarly you can see the coefficient, standard error and all. Now let us check the sum of squared error by predicting values of y for test cases and subtracting from the actual y for the test cases. So MSE equals to np dot mean regression model dot predict x test minus y test multiplied by 2. Now under root of mean square error is standard deviation, that is average variation between predictive and actual, right? So importing math here, math dot square root of MSC, so we are getting 3.053 nearly. So there is average of 3.0 round of MPG different from real MPG on an average. Now predicting mileage MPG for a set of attribute not in the training or test set. Now y prediction equals to regression model dot predict x test. So since this is regression, plot the predictive y values versus actual y values. So for the test data, a good model is prediction will be close to actual leading to high R and R2 values, right? So here we are plotting the scatter plot again for y test MPG and y prediction. So here you can see that. Now how do we improve this model, right? And the R2 is basically we have is stating here is 84%, right? Now how do we improve it? So this is basically for iteration 2 that we are going to do here. Now from scipy.stats import z-score mpg-df scale equals to mpg-df dot apply z-score. Now convert the numpy array back into a data frame. So mpg-df scaled equals to pd dot data frame, mpg-df scaled equals mpg-df scaled, then column equals to again df dot columns. Now if we browse the contents of the data frame, right, so here we are getting mpg-df scaled, right? So here you can see all the z-score that we have for the respective columns, right? Now next thing what we have is copy all the predictor variable into x data frame. Since mpg is a dependent variable, drop it. So x equals to mpg-df scaled dot drop mpg, x is equals to 1. So x equals to x dot drop origin America, origin Asia, origin Europe, x is equals to 1. Now copy the mpg column alone into the y data frame, and this is the dependent variable. So y equals to mpg-df scaled mpg. Now split x and y into training and test set in 75 by 25 ratio. So x train x test, y train y test, again train test split with 30 of test size and 70% of train size, and random state again we are passing an integer. Now invoke the linear regression function and find the best fit model on training data. So regression model equals to linear regression, right? Regression model dot fit equals to x train y train. Now linear regression, copy x equals to true, fit intercept true, and jobs equals to 1, normalize equals to false. So let us explore the coefficient for each of the independent attribute. Now for idx column name in enumerate, right, we are enumerating it for getting all the coefficient. So if you compare this coefficient with the last one, you will definitely get the slight difference, right, in cycle, in car types. Okay, now intercept, regression model dot intercept for 0, right? The intercept for our model will here is it is 0.16% we can say. Now regression model score, so for x test y test it is 84%. Let us check the sum of squared error by predicting values of y for training cases and subtracting from the actual y for the training cases. Here MSC equals to np dot mean, right? Regression model predict for x test y test, again multiplying with 2, understood of under root of mean square error is standard deviation, that is again average variance between predicted and actual. So again doing the same thing for SQRT of MSC, right, mean square root error. So it is we are getting that at 39%. Now predict mileage MPG for a set of attribute not in the training or test set. So y prediction equals to regression model dot predict x test, right? Since this is a regression plot, the predicted y values versus actual y values for the test data, a good model's prediction will be close to actual, leading to high r and r2 values. So plt dot scatter, that we are getting y test mpg of and y prediction. So here you can see that the scatter plot, finally we got the positive correlation in it, right? So yeah friend, this was all about this FMT video number 4. We will also come up with the next video with more interesting facts and case study. So stay tuned. All the best for your AI journey. Thanks. Have a good time.